Hello and welcome to CE 407 Separations. This course is the course where you learn all about the separation methods that chemical engineers use a lot in real practice, such as distillation, gas absorption, stripping, liquid extraction, really useful stuff, which I'll get into in a few moments. My name is Johannes Nietzsche, and I'll be presenting the lectures for this course. Some of them will be live lectures like this one. Some of them will be PowerPoint presentations. A lot of them will be me talking in the background, working through problems, because ultimately this course is a course about solving problems and getting competent in doing useful work in designing pieces of separations equipment. A lot of the material was prepared by Dr. David Kortmansch, also in our department, so you'll be seeing a lot of material from him. So a few general comments before we start. The first thing is that when you think about what chemical engineers do, I can't say it's exactly half-half, but a lot of chemical engineers get involved in large-scale chemical production. So that's huge oil refineries, production of bulk commodity chemicals, which basically powers the whole world. And that's what this course addresses. The other sort of half of what chemical engineers do is making all kinds of products. For example, a drug patch, or making plastic bottles, or maybe some kind of paint, or a food product, or something like that. So when you think about what chemical engineers do, half of them do a lot of work on products, and half of them do a lot of work on big, large-scale chemical production, and that's really what this course addresses. So when you think about what chemical engineers do, there's that word chemistry. So you think of huge chemical reactors that are creating some kind of chemical product that you want, and that's absolutely true. But the reality is that what comes out of a reactor very rarely, in fact, essentially never, is the pure whatever you want, chemical that you want. Typically, it's a horrible mixture, a mess of what you want, the product, from all sorts of byproducts and other things, and unused reactant. And so to get the product that you want, you have to separate it from all the other stuff that you don't want. And that's why separations is very important. If you look at any typical chemical plant and count the number of pieces of equipment, or could somehow weigh the tonnage of equipment, or we're flying in an airplane and look down at a map and look at the acreage that's covered by different pieces of equipment. Even though a chemical plant typically runs some chemical reactions, in terms of the sheer mass or amount of equipment, usually there's more downstream equipment, which is separations, to clean up and purify after the reactor than all the reactors combined by themselves. Plus, there's the other element that for environmental preservation, there's all kinds of other separations equipment, which is just in any chemical plant, because you can't be taking contaminated air or contaminated water and just dumping it into the atmosphere or into the river. And so aside from everything else I've said, there's just so much equipment, for example, scrubbing towers to clean up air that's released into the atmosphere. So for both those reasons, separations is very, very important, just because of the number of separations jobs that have to be done. Even though when you think of chemical engineering, you think of huge reactors when you're talking about large-scale chemical production. Oftentimes we will be referring to a solute in this course. That's the thing that you're interested in. Sometimes you're interested in the solute because it's what you have produced. It's the chemical that you want, that you're trying to purify. Other times it's something bad. It could be something toxic. For example, it could be ammonia that you want to get out of air, so that you can, you certainly don't want to be breathing ammonia. Or it could be a sulfur dioxide or something like that. It could be some contaminant in water that you have to clean out before you return water to the river, say. So we're interested in the solute, the particular chemical species, for one of two reasons. Either we want it, or it's toxic and we don't want it to be there. So that's two reasons why you might do separations. That's aside from the fact that you're doing separations to purify your product. This course, I sort of feel, almost teaches itself. It's just so much fun because you're putting together knowledge from CE 212 in our curriculum, which is the Introduction to Chemical Engineering, or Fundamental Principles, or Mass and Energy Balances, using a lot of thermodynamics knowledge, In our curriculum, that's CE 304. If you're at another university, it might be called something else. You're also using a lot of mass transfer, which here is CE 318. Now, I've got a little asterisk by that in my notes. The mass transfer for much of the course is kind of hidden. And in fact, when you do your typical analysis of say, a distillation column or a liquid extraction column or set of mixer settlers or any kind of separations process, sometimes you don't run across the mass transfer even though it's there. And so actually, we're going to talk formally about mass transfer about halfway or a little bit after into the course, and we'll be explaining the reasons for that. But so even if it doesn't look like it at the beginning of the course, mass transfer, which is what you simply see in a heated mass transfer course, is actually happening a lot, even though for at the beginning it'll be kind of hidden. You draw really cool diagrams. For example, when you design a distillation column or liquid extractor, you do a McCabe-Thiele diagram or an operating diagram. And the same thing holds for absorption. It's almost more fun than solving puzzles. And people go on the internet or buy little books and buy crossword puzzles and other things like that. And just doing this course, you're drawing all kinds of neat pictures and doing calculations, and it's just pure joy and almost more fun than entertainment that you actually spend money on. Let me say a few words about this book. So we're using the latest available edition, the 7th edition of Unit Operations of Chemical Engineering. Look at those authors, McCabe, Smith, and Heriot. Big names and historical names in chemical engineering. This is a classic tome, which is, I'm holding pure greatness in my hands. It's a real classic. The first half of this book deals with fluid mechanics and in unit ops terms, flow through pipes and pumps and so forth, and heat transfer and heat exchangers and evaporators and things like that. And then, so we're actually coming into the second half of this book, and we're in this course going to cover about half of that. So it's the second half of the book where they really get into mass transfer and separations, which is the topic of this course, and we're going to be covering about half of that. And I can be very concrete. We're going to be starting on page 521 in the 7th edition, and the first section is kind of an introduction to this part 4. So the second half of the book starts with part 4, and that is starts on page 521, and there's about 5 pages, 521 to 525, of an introduction to this part of the book. You know something? Let's just look a little bit at this part of the page in the book, and I've printed out here for myself. And I'm just going to read a little bit from it because it is just so well written. So, a group of operations for separating the components of mixtures is based on the transfer of material from one homogeneous phase to another. So transfer of material. So there's transfer or transport going on. So clearly mass transport all over this course. Unlike purely mechanical separations, these methods utilize differences in vapor pressure, solubility, or diffusivity, not density or particle size. So it's a chemical affinity for, say, the liquid phase or the vapor phase, some microscopic interaction which is causing the separation to happen here. The driving force, another important word, for transfer is a concentration difference or a difference in activity, much as a temperature difference or a temperature gradient provides the driving force for heat transfer. Very well written sentence. We're always talking about driving forces. A system is not at an equilibrium state, and the driving force or the departure from the equilibrium to relative to the equilibrium state, that's what really drives transport. These methods covered by the term mass transfer operations include such techniques as distillation, gas absorption, dehumidification, adsorption, liquid extraction, leaching, crystallization, etc., and a number of others not discussed in this book. So that one paragraph, I can't believe how well this is written, really gets across the subject of this book, and actually it's loaded with some technical terminology, and you kind of have to have done this course, and then when you return to this material, read it, and you see the depth of actually what's written here. And it says a few words about the first two separations that we were going to be talking about. Let me skip to the second one. So, in gas absorption, a solute gas is absorbed from an inert gas into a liquid in which the solute is more or less soluble. The washing of ammonia from a mixture of ammonia and air by means of liquid water is a typical example. Good example, because I certainly would not want to be breathing in a lot of ammonia. And the second unit op we're going to be talking about, the separation method, is distillation. The function of distillation is to separate by vaporization a liquid mixture of miscible and volatile substances into individual components, or in some cases into groups of components. So again, very well written sentence, kind of loaded words there. So I have to say a couple words about reading. First, we should appreciate the fact that this is really a sterling book, just a remarkably well-written book. Some of the material is complicated, and especially some of the diagrams, you have to read through the derivations carefully, look at the graphs carefully, or the figures carefully, to really understand what's going on. This is high-level scientific reading, and you will find that the first time you read something, you may not understand it. And in fact, you generally don't, and that's completely normal. So, plan on reading, making a first pass through any particular part, chapter, say, or part of the book you're reading. Read it once, just to get a feel for it, and some of the stuff you'll understand, and then read it again, and then read it at least one more time. So in other words, plan on reading the book at least 3 times whenever any particular part of it, because the first time you're sort of getting acquainted and jumping in and looking at the material. And the second time you're starting to understand it and work through the derivations. So only the third time do you really understand what's going on, to the point where you can really do problem solving, which obviously we'll be emphasizing in the homework. And I'm kind of not kidding. I'd recommend that after you finish every chapter, return to this beginning of section 4, again page 521, just this 5 pages, and you'll begin to see more and more how remarkably well it's written. Some things the authors can't just blurt out because the concept hasn't even been introduced yet. But I think it will really help your understanding if every time you close down another unit operation like gas absorption or distillation, come back to the beginning of the book and read it and let it wash over you and just revel in the remarkable prose that's here, and not only because it's remarkable to read, but also because it'll help your understanding. And I have to say, I can't say enough about how well this book is written. So I've got here some other books. So here's a piece of the collected works of William Shakespeare. Here's David Copperfield by Charles Dickens, and here's a collection of some literature which includes Heart of Darkness by Joseph Conrad. And I have to say, I'm looking at these books, and here's McCabe and Smith unit operation, McCabe, Smith and Harriot unit operations of chemical engineering, and here's all this literature, and you read this stuff, and ultimately you come down on, this is just carries more weight and is just so remarkably written. It's actually more literate in literature than these books over here. That's how well it's written. So we got a really great book here. And something, when I think about this, these books, compared to this one, they're just not good enough. That thump that you heard was me throwing those books in the garbage because I'm just not interested in those books, considering that I've got this book in my hands that I can be looking at. It's so well written. Okay, so let me just say a few words about gas absorption, which is the first separation method we'll be talking about. Just look at what I'm erasing here. You take this course, how can life be so good? That's the question I always ask myself. I asked it when I was learning this myself, and I ask it every time I teach this course, how can life be so good? Okay, let me just talk through a little bit the first separations process we'll be talking about, which is gas absorption. And that typically happens in a tall tower, which is this cylindrical thing around here. I'll just draw it as a rectangle seen in cross-section. But let's just talk this through to get the main idea across what typically happens in a separation. So let's say we have an airstream, but it's contaminated. So we have air here, but it's contaminated with some solute A. A could stand for ammonia, for example, and I certainly wouldn't want to be breathing a lot of ammonia. So we like to remove the ammonia from the air. And the purpose of gas absorption or gas scrubbing is to clean up a gas, very oftentimes it's air, which has something in it that we wouldn't like to breathe or that's toxic for whatever reason. So we pump it into the bottom of the tower. I'm just going to call the bottom end of the tower B, but B doesn't stand for the first letter of bottom because I'm just going to call the top of the tower A, and there's no commonality letter there. So, what's supposed to happen here? Well, I just like to get rid of the A in the air so that when the air flowed out the top of the tower, there was much less. And so I'm going to say the air here, and I'm going to put a tiny little a here because ideally that will be a very small amount. So we'd like to get the A out of the air, and the way that's often done is with gas absorption or gas scrubbing, which is contact with a liquid. So, and if we're talking about ammonia, a good way to remove ammonia from air is to contact it with water. So there's water coming in. And let's say the water comes in clean, so there's no ammonia here. But by the time it flowed down the tower, we would like the water to have picked up or absorbed a lot of the ammonia, so that we'll have whatever water was here, but we'll have a significant amount of ammonia. So this water did our absorption or scrubbing. It picked up some of the ammonia. So this is clearly an idealization. The air is going up the tower, the liquid's going down the tower. I certainly don't believe that the air is going to stick to the right half and the water is going to stick to the left half. That's ridiculous. But let's just, as an idealization, say that there's a certain collective interface. There's gas on one side of some interface and water on the other side. And the purpose of this whole absorption tower is to get A to go from the gas phase to the liquid phase. And A actually wants to do that. Because if you give an ammonia molecule, say, a choice of being in the gas or water, air or water, it has a preference, certain preference for air, and it has a certain preference for water. And if the water that comes into this tower is completely clean, some of the ammonia would like to be there. Now, an individual molecule is not a sentient entity with power of choice. When you say a molecule wants to be there, what you really mean that it's energetically favorable for it to be there. And if you just have a system and let it relax to equilibrium, be the way it wants to be from energetic considerations, some of the ammonia will actually want to sit in the water. So that's how gas absorption works. You pump air at the bottom of the tower. Clearly water flows down, it's heavier, so you just pump air in the top of the tower, it flows down, there's a lot of contact. I've drawn this as a wavy interface, a lot of opportunity for the ammonia, if it wants to, and it does want to get from the gas phase to the liquid phase. And so if some of the A moved into the liquid, it got out of the air, and there's less left, and the air got cleaned up. So that's really the purpose of gas absorption. Now why did I say all this? Well, the key to separations very often is to get two different phases to contact each other. Because in real life, you cannot have a tiny set of tweezers and be picking out individual ammonia molecules or any A molecules from air or anything like that. That's ridiculous. That just doesn't happen. That's not possible. But if you contact the air, which is a gas phase, with an other phase, a liquid phase, and have some of the A move over there because it's energetically favorable for it to do so, then when you separate these phases, in this case it happens because the water just runs out the bottom, some of the A has been literally taken away. So you can't individually take A molecules from a gas and pull them out, but if you can get A to go to a second phase, which is easy to separate, and let's face it, it's very easy to separate a gas from a liquid because the liquid is about 1,000 times as dense as the gas, and it just happens by gravity. If you can get any A or any component from one phase to another phase, then separating phases is very easy to do. So one of the keys to separations is to employ two phases and have some preference of what you're interested in, A, ammonia, or whatever, for one phase relative to the other phase. So in a nutshell, this kind of tells the whole story of how separations work. If you can get a molecule to distribute between two phases, then you've got a shot at separating are getting some of it out of one stream, say an airstream, because two phases generally have very different properties and are easy to just bodily separate one from the other. So it's this happens to be gas absorption is the first unit separations method we're going to be talking about, but that really gives an idea of kind of the overall scheme of the idea and why it's so important to have material in two different phases. I'd like to list some things for you that you should watch for and that you should be aware of, and kind of to calibrate your whole approach. The first one is that clearly there's, you're reading a book and there's a lot of lecture material. What you're ultimately interested in is solving problems. So there are no homework problems in this course, do this derivation, or write an essay on how great distillation is, which would be a very nice story to write, but we're here to solve problems. And you notice that all the homework is problem solving. The homework will prepare you for the exams. The exams are very problem solving. So our goal is to be effective and competent in solving problems. So this is a problem solving course. Kind of in terms of overall concepts, just so that you understand what's going on and don't get confused, there's a couple of distinctions to watch for. The first one is this distinction between batch and continuous operations. So a continuous operation is something that runs at 1,000 pounds per hour, day in, day out, ideally, although every so often something goes wrong, or every so often you have to do maintenance on a chemical plant. But continuous processes run at a constant rate all the time. And actually, I want to say most separations actually, especially if they're large scale separations, are done in continuous mode. But there are some separations which either when you run them at small scale it becomes advantageous, or they're inherently batch, which means you start a process, you put something in a piece of equipment, and then it runs, and then you stop, and then you get out the material that you want from there. So most of the operations are continuous, but we'll also be talking about batch processes. So you want to keep in your mind the distinction between continuous and batch processes. The second concept is the difference between packed and tray towers. So I haven't said what's inside the tower, and there's two approaches that are used. In one approach, you have individual trays, and the liquid literally flows down the tower, goes across this tray, then goes into another little channel, which is called the downcomer, and flows down to the next tray and so forth. So it takes a zigzagging path. And similarly, there's a gas phase which is going up in holes in these trays. And when it rises through the liquid, it makes bubbles, and there's lots of mixing and froth. But the key thing here is that the contact happens on individual trays. Tray number 1, tray number 2, tray number 3. And that's an inherently discrete process. And a lot of separations are done in that way. But sometimes if you would open up a tower, you would look inside and you wouldn't find any trays. You would just see that somebody had dumped in what kind of looks like, say, potato chips for packings. Clearly they're not made of styrofoam. They're probably made of either metal or some hard plastic or ceramic. But it's just, I'll just draw them as little beads here, although they can have very complicated shapes. And they're just dumped in there. And there's no, it's just a continuous mass of all these beads. Those are called random packings or packed towers. And the contact between the liquid going down the tower and the vapor going up the tower happens in this random packing. So those are two inherently different approaches. And so some of the processes we'll be talking about, especially in the first half of the course, are stage-wise contact, which happens on individual stages or trays or plates, they can be called. And that's just inherently different from what happens in packed towers, where they have dumped in them a random packing. So in the separations process, these we're going to be talking about, keep a watch for what's happening in a tray tower or by stage-wise contact, and what's happening in a packed tower, although there's no secret, and it's not hard to figure out in the first part of the course. Roughly the first half, we'll be talking all about stage-wise contact, where contact happens on individual discrete trays, and then we'll be shifting gears. And one of the reasons I mentioned that is that mass transfer is happening in both versions of these kinds of separations, But here it's kind of hidden for reasons that will become clear, and you don't seem to be doing mass transfer, whereas here you do the analysis and it's very clear you're doing mass transfer from the get-go. And I think it's pretty clear that A, this mass of A, or the moles of A, are transferring from the gas phase to the liquid phase, so there's clearly mass transfer going on, but you don't seem to be using a lot of the theory what you learned about diffusion and your heat and mass transfer course. It's actually going on, but it's kind of hidden. So I just want to make you aware of that. So keep in mind not only the distinction between, say, stage-wise contact, contact in tray towers and contact in pack towers, but what's really different about those two approaches is that here the mass transfer is hidden, whereas here it's obvious from the get-go. I'll just make one other comment. So oftentimes in the gas phase, you call mole fractions Y, so I'll always be calling the mole fractions in the gas phase Y. In the liquid phase, you call them X. In liquid-liquid extraction, which of course we'll be getting to, there are two liquids which don't mix. And that's, it's not a gas and a liquid, which clearly don't mix because one is 1,000 times as dense as the other, but we have, in common experience, exposure to all kinds of situations where you have two liquids that don't mix. Any kind of water and any kind of oil don't mix. And so in liquid-liquid extraction, you have two phases. One of the phases is called X, one of the phases you call the mole fractions Y, and that doesn't mean there's a liquid and a gas, but we just call them X and Y anyway. So be aware that there's always two phases, although they may not be liquid and gas in some of the separations that we're doing. So now I'm going to say a few words, not live lecture, but showing you the website, because the website is a very good resource for this course, and I want you to introduce it. And I would spend at least half an hour today kind of nosing around the website and looking at the homework page and the notes page so that you're familiar with all the material that's available for you.